right, welcome back to the second talk, which is by Chris Manon. He will talk about toric matroid bundles.
All right. So the title of the talk is Toric Matroid Bundles, but it's it's about a collection of objects that we're not quite sure what we're going to call yet. So it could also be called Tropical Matroid Bundles or Toric Tropical Matroid Bundles. I'm not sure. But this is all work that's joint with QMARS Cave. Okay. So hopefully by the end of the talk, this can be a question that you all here can consider. So the theme of the talk is that some cool people put matroids into algebraic geometry, and then like good stuff came out. And I'll tell you a bit about that good stuff. And so my question for you is, can you put matroids in topology, and can more good stuff come out? So maybe have that in the back of your mind during the talk. The purpose of the talk is to explain the construction of a matroid bundle. And so here's my picture of a matroid bundle. The idea is it's like a fiber bundle, or in particular a vector bundle, over a particular type of space, and that space is a toric variety. All right, so matroids are these discrete objects. So what does it mean to have them in a family? So these are the questions about matroid bundles that I hope to answer by the end of the talk. How do we do this? How do we put discrete objects into a kind of continuous family? And well, why would we do that? Okay. So first I'm going to recall some stuff about matroids. We heard a lot of good stuff in Chris's talk, but it never hurts to hear things again. Also, matroids come in about 3 billion different guises, and so maybe you'll see a little bit of a different side of them in this introduction. So matroids are a structure on a set. For us today, the set is going to be E, and it's going to have M elements, M for matroid. And then to begin with, a matroid will be a rank function. So this is a non-negative integer valued function on the power set of E, and it has to satisfy some rules. And any non-negatively valued function on the power set of E that satisfies these rules is a matroid. So here are the rules. Rule 1, the rank of a set needs to be bounded above by the size of the set. So matroids are made to sort of generalize the columns of a matrix. So when you think of a set, it should be thought of as like a collection of columns in a matrix. And what this is saying is if you take the span of the columns of a matrix, the dimension of the resulting space is always less than or equal to the number of things you spanned. Right? That's the intuition behind this first axiom. Secondly, we need submodularity. So what this means is if you take two sets and you compute the rank of the union and the intersection and add them, you get something that's bounded above by the ranks of the two sets you started with. So what's going on here? Well, once again, think of the columns of a matrix, and now imagine them as points in space, right? And now take the span of one collection of points and the span of a second collection of points. Those two spans are now linear subspaces which may intersect, right? But just because the spans intersect doesn't mean the points that you use to make the spans intersect. That's pretty much why submodularity. And then the third axiom is that if you add an element to a set, it can only increase the rank at most by 1. So either a vector is a linear combination of other vectors, or it isn't. That's the idea. All right, so this is a rank function. Like I've been saying, if you take an actual matrix over an actual field, then you can get a rank function for free. That rank function is you send a subset of indices S to the span of the vectors, the columns of that matrix with those indices. That will always be a rank function. And the matroids that come about this way, where there's some matrix over some field out there, maybe K, where the rank function coincides with this function, you say that they're representable over K. All right. So now I want to tell you about some polyhedral invariants, or maybe polyhedral cryptomorphisms of matroids. So I'm going to tell you about two different ways you can make something polyhedral out of the data of a matroid that captures basically all of the matroid in both cases. Right? So a subset of this ground set E is said to be independent if the rank drops whenever you remove an element. So once again, think about a collection of independent vectors. And then a maximal independent set is called a basis. And then it turns out all bases have the same size, just like if you take a matrix and you take the span of all the columns, some subsets are going to be bases of that span, and they're all going to have the same size. All right, so that's what a basis is. It's a maximal independent set. So for any subset on the index set, we can form the indicator vector. Right? We sum the fundamental basis vectors that come from that set. And if we take the indicator vectors of bases and arrange them in space, and take their convex hull, we get a polytope. And that polytope's vertices are precisely the basis vectors you started with. That's called the base polytope of the matroid M. And you can recover the matroid M because you can recover the bases from the matroid polytope of M. All right. So this is a way of uploading combinatorial theories like Earhart theory and also the geometry of toric varieties into matroid theory. There is a polytope now. All right, second polyhedral invariant of a matroid is going to be the Bergman fan that we heard about in Chris's talk. So a flat is a subset of the index set with the property that anytime you add an element outside the flat, the rank goes up. So think of a flat as what you get when you take a linear subspace and intersect it with your collection of vectors, right? By definition, if you added a new guy outside of that linear subspace, it would go up in dimension. So that's the intuition behind a flat. And then a complete flag of flats is just a collection of flats where all of the ranks are represented and they include each other in the way they should. So an increasing chain of flats where the rank goes up by one on each step. So for any complete flag of flats, we can form a cosimplicial cone. And here's how we make it. We take the indicator vector of the whole set, the all ones vector, and we take the line through it. And then we add the positive span of the indicator vectors of the flats from the flag. Right. And this is a nice cone in Rm, and these form the maximal faces of the Bergman fan of the matroid. And it is important, like we heard in Chris's talk, that we consider this not as just a set, but as a fan. All right. So now we have a polytope and we have a fan. Now let's see an example. So this is also an example, I believe, that was in Chris's talk. So here is the matroid U23. It's the uniform matroid of rank 2 on 3 elements. So anytime you take an index set and you make the bases all the sets of a fixed size, that always forms a basis system and is a matroid. So this is when you take all of the subsets of size 2 and declare them to be bases. And the rank function is that the empty set has rank 0, the singletons have rank 1, the pairs have rank 2, and then everything above has rank 2 because the pairs all make bases. All right. So like I said, a basis is a set where if you remove, it's maximal with the property that if you remove any element, the rank drops. And so these are easily seen to be the size 2 sets. And so what you see here is the convex hull of the indicator vectors of all sets of size 2, and it's a triangle. It's kind of a weird looking triangle, and I'm not quite sure why, but I'm not an artist. Okay. Second up, we have the Bergman fan of the same matroid, U23. So looking at the lattice of subsets in the rank function, we need to remember for sets that when you add any element, the rank goes up. So none of these guys are going to be flats because the rank doesn't go up when we add the missing element of the set. However, each singleton makes a flat because adding any other singleton makes the rank one more. So the flats here are like the whole set, the empty set, and these singletons. So a complete flag of flats will really just be determined by which singleton it contains. And the indicator vectors for the singletons are just 1, 0, 0, 0, 1, 0, and 0, 0, 1. And so we end up with this picture. We get the line through the all ones vector, and then we span out in each fundamental basis direction. It's also usually interesting to consider this Bergman-Fann's image under the quotient by the all ones vector. And when you do that with the Bergman-Fann of U23, you get the picture that you're required by law to draw if your talk includes any tropical geometry, the trinion. So. Well, it's the one skeleton of the fan for projective space. If you associated a toric variety to this fan, it would be a 2 torus with 1 tori stuck in at 3 places, but no fixed points.
Can you tell that from the previous before you draw the fan?
Can I tell?
Is there some connection before you draw the fan?
Sort of. Maybe that will get answered when I talk more about how it's related to the permutahedral variety. Okay. So last, I want to tell you about degenerations of matroids. So I don't think we've heard about this yet. So the idea is that, here's how I think of the Bergman-Fann. It's a collection of directions where if you fire the matroid off in those directions, you get another decently related matroid to your original matroid. So for any direction in the Bergman-Fann, you can form something called the initial matroid. And what you do is, it's very algebra 2 in the States, or it's very linear optimization. You take that direction and you look at the face of the matroid polytope, which maximizes that direction. The vertices of that face will then form a basis exchange system, so a matroid. And that's the initial matroid. All right, so that's the idea behind the initial matroid. So here's the example, combining the two pictures from before. If we take 1, 0, 0, which is one of the directions in our Bergman-Fann, and we maximize it on the matroid polytope, we get this edge 1, 1, 0, and 1, 0, 1. And those two sets form a basis system for the matroid U11, uniform matroid of rank 1 on 1 element, and U12, the uniform matroid of rank 1 on 2 elements. If you direct sum those two matroids, that's the initial matroid. All right, so the Bergman-Fann is a collection of directions that we can degenerate our matroid into a new matroid. So this kind of makes matroids feel a little bit more topological or geometric. Now they have some wiggle room. They're not just a discrete thing. They have nearby discrete things too. All right, now let me tell you about a non-polyhedral invariant. Now we're going to get into the motivation for this idea. I'm going to tell you about a non-polyhedral invariant of a matroid. It's called the characteristic polynomial. What you do is you sum over all subsets of your index set, and you put a -1 to the size of the set next to a variable to the rank of the matroid minus the rank of that set. So it's deduced from the rank function. And when you collect terms, you get coefficients that are alternating in sign. And the Heron-Roda-Welsh conjecture was that if you fix an index I and take the absolute value of the coefficient and square it, it will be bigger than the product of the absolute value of the one before and the one after. And this is called log concavity. All right, and this was resolved by Adda-Presido, Hu, and Katz. And as a result of one of these ways of modeling a matroid with things from algebraic geometry. All right. So the idea is to interpret the coefficients of actually not the characteristic polynomial, something called the reduced non-sign characteristic polynomial, but you can deduce one from the other, as intersection numbers. So this is a part of intersection theory and algebraic geometry. The phrase Chow ring can be associated to it. So you think of these coefficients, you show these coefficients coincide with certain intersection numbers in the Chow ring of the matroid. So this is a kind of a Stanley Reisner looking ring. It's a ring over one variable for each proper non-empty flat. You impose the relations that the product of two generators is 0 when the flats are incomparable. That is when one doesn't contain the other. And you also impose the relation that if you pick two elements of the matroid, let me zoom in on this, pick two elements of the matroid, and you sum over all the flats that contain one, it has to equal the sum over all the flats that contain the other. And that element that you get, the uniquely defined element that you get by picking any element and doing this, is called alpha. And the sort of complementary element, the one that you get by summing all the flats and removing alpha, is called beta. And these are these two classes whose degrees of various powers realize the coefficients of the reduced non-sign characteristic polynomial. So this is what they proved. They proved that these degrees are log concave. So how do you do that? So the idea is that it follows by constructing a combinatorial analogy with results from the intersection theory of smooth projective varieties. So you show that the Chow ring has Poincare duality, you show that it has something called the Hard-Lefschetz property, and you show that it satisfies Hodge-Riemann relations. And then you establish that this alpha and this beta are something called Neff classes. So if you've ever heard what an ample line bundle is, an ample line bundle defines an ample class, and the limit of ample classes is a Neff class. That's how you can place Neff classes, and maybe something you've heard about. So you can read more about this in, I really like the paper by Matt Baker, Hodge Theory and Combinatorics, and then the books by Lazarsfeld, Positivity and Algebraic Geometry, develops this intersection theory from the algebraic side. That's right. And this project is what Junho got the Fields Medal for. Okay, so now I want to tell you about some related work by Birgit, Spink, and Seng. So what they do is they make this analogy with geometry stronger by recasting both this geometric model and other geometric models of matroids in terms of the Chern classes and K-class of certain vector bundles on a certain toric variety, the permutahedral variety. So they show that these cool intersection theory properties can emerge from the positivity properties of certain vector bundles. All right. So in particular, if M is representable, they construct a pair of globally generated vector bundles. Global generation is positive. We like it because it means that the sheaf of sections can be, extracted from the top, the global sections. When M is representable, they construct globally generated bundles. They call them QM and SM dual. SM dual is the dual to another bundle called SM on the permutahedral variety. And then there are positivity properties in general from globally generated bundles that imply log concavity results for various matroid invariants related to the Tut polynomial. So it's like we have a positivity theory in algebraic geometry. This allows us to use it on matroids. And then they extend this definition by using some technical equipment to all matroids. So this is getting closer to what I actually want to talk about. So when M is representable, there are actual geometric objects out there, actual vector bundles on an actual complex, algebraic variety, which sort of lie behind the positive intersection theory properties that we need. And the question is there geometry behind the non-representable ones? So a quick aside about representability and non-representability and its relation to geometry. Bergman fans of matroids are precisely what are called tropical linear spaces. And the Bergman fans of representable matroids are those tropical linear spaces. So tropical linear spaces are an abstract combinatorial thing. They're a fan with a certain weighting system on them. But the ones that come from representable matroids actually emerge from tropicalizing an algebraic linear space. And we heard about that in Chris's talk too. So, a vector bundle is made out of actual algebraic linear spaces. So if we want to increase our language to see the non-representable ones, we need geometry that allows us to fit into that place. And perhaps the Bergman fan of a matroid is then that geometry. So this suggests that the geometry that we want to find to make the right kind of bundle that gives rise to the right kind of characteristic classes should be some kind of tropical bundle. But it needs to have enough information in it that it still produces Chern classes and K classes. Right. So that's the idea. So I'm going to tell you about how to construct such an object. But I'm going to review a little bit first about toric varieties. In particular, how I like to see toric varieties. So as a reminder, a toric variety is, this is a silly way to say it, it's a T-equivariant partial compactification of an algebraic torus. Algebraic torus is a product of C stars. I'm going to take it to be C star to the D for dimension. And any algebraic torus comes with two free abelian groups. Two free abelian groups for free. One is the lattice of co-characters, that is the ways to stick C star inside the torus. So these are one parameter subgroups. These are pads in the torus, right? And then the other one is the dual lattice of that lattice, which is the lattice of characters, ways to map the torus down to C star. So M is like the coordinate ring. It contains information of the coordinate ring of the torus. And N contains information, like I said, of these curves inside the torus. And the fact that there's a pairing is like the cool thing that you use to get a lot of the combinatorics of toric varieties to tell you things about algebraic geometry. So the one-dimensional things and then the maps. Right. Okay, so as is known, toric varieties for a torus T are classified by integral polyhedral fans in the co-character lattice. So a lot of times you hear about polytopes in toric varieties. The polytope is really an M-side object. The fan lives on the N side. So the fan divides the co-characters of the torus up into families that have a nice property with relation to the geometry of the toric variety. So the relationship between the faces of the fan and the geometry of the orbits of the toric variety is reversing. It's dimension reversing. So the biggest faces correspond to the smallest orbits. So here I have a complete fan, so I get a complete toric variety. The faces sigma 1 through sigma 5 correspond to the fixed points, P1 through P5, and then the rays, tau 1 through tau 5, correspond to the divisors, the irreducible reduced divisors. All right, so here's what I really like about the fan description of toric varieties. It tells us how limits work, tells us how to go to infinity. Who doesn't like going to infinity? So if you pick a co-character from a face of the fan, sigma 2 in this case, but sigma, what you know then is that the limit of that co-character, remember this is a curve, and the limit of that curve will lie in the orbit corresponding to that face. That's what the fan tells you. So in particular, if I pick N, it lives out in this face sigma 2. This is a co-character, so it is a one parameter curve inside my torus. I take its limit, and I know that because I picked it from sigma 2, that limit falls into the fixed point. So this tells you that a sort of randomly selected co-character's limit is in one of the fixed points, and you have to be a little bit more careful about how to get one that lands in a higher dimension boundary component. All right? But that's what I like about the fan. The fan is how you go to infinity. Okay. Just to make a connection with what many of you know about polytopes and toric varieties, if you have a polytope, you can form what's called its inner normal fan. So what that means is you go to the facets, you take the inner pointing normal vectors, you span out the rays in those directions, and then you form the the hull of the rays whenever the corresponding facets have a non-empty intersection. So if I take, for example, this ray and this ray, they intersect right there, and so I fill in that column. And that's how you get the complete fan associated to a polytope. But once again, the polytope really lives on the M side of things, and the fan lives on the N side. So an example of this, here's a fun way to get a polytope. Pick a general point in Rm, and really think about it as a point in Rm mod the all-ones vector, and act on that point with the symmetric group. So just translate it around, and you get m factorial different points. Take the convex hull. That's a polytope. Now take the internormal fan, and you get the internormal fan of the permutahedral variety. So that's this permutahedral toric variety that I've mentioned a few times. So here's a hexagon. That's a permutahedron, right, for 3. All right. So now I'm going to tell you the idea behind toric matroid bundles. How do we make a bundle over a toric variety out of matroids? And hopefully we do it in a way where we actually capture geometry. So here's the idea. There have been 2 objects in this talk where I've told you how to go to infinity. The fan tells you how to go to infinity in the toric variety. The Bergman fan tells you how to go into infinity with a matroid, right? So to make a toric matroid bundle, you just match up the 2 ways to go to infinity. I tell a co-character how to take the matroid over the identity of the torus and send it to the boundary, literally by making a map between the fans. All right. So here's a picture of what I'm talking about. If I pick a co-character P, right, I know because I picked it on this ray that it's going to go to this toric divisor. I'll go to a special point on that toric divisor. And what do I stick above that point? Well, I stick the initial matroid for wherever psi told me P is going. All right, so the way you can imagine these things is over the big dense torus, it's all the matroid M. And then when you pop into the boundary divisors, you just take these initial matroids. All right. That's what a toric matroid bundle is. Of course, this needs to happen in some sense of a continuous way, so this isn't just any old map, it has to be a special type of map. I'm going to avoid saying all of the properties it needs to have, but we can just call it piecewise linear. That's a legit thing to call it. So it's a piecewise linear map from the fan to the Bergman fan. And if you're familiar with the divisor theory on a toric variety, you know that a Cartier divisor, which corresponds to a toric line bundle, is a piecewise linear map from the fan to like the real line. So if you replace the real line with the Bergman fan, you turn line bundle into matroid bundle.
What does ample have to do?
So the Cartier divisor is ample if it's strictly convex. So it's a property of the piecewise linear function. And actually, Kumars and I know that we've shown that in this setting, ample and for related objects to this, ampleness and global generation can be captured by similar piecewise linear properties. All right. So this can even be simplified a little further. It turns out everything is determined by where the ray generators go. It's a consequence of this piecewise linearity. So I'm going to let n be the number of rays. Then all you really need to know is where psi sends the rays. And as long as you have a smooth fan, that is the faces of the fan, actually probably just simplicial. As soon as you know where the rays go, you can cook up a piecewise linear map, as long as you've done it in a nice designed way, which I'm brushing under the rug. So all of the data of a toric matroid bundle can then be captured in a pair. That pair is the matroid M, which you think of as the fiber over the open orbit, and then this matrix D. It's an N by M matrix, N for number of rays, M for number of elements of the matroid, which contains all the data about how to send it to infinity. And all this matrix needs to do is satisfy some design properties, and you have yourself a toric matroid bundle. So in particular, the rows need to be satisfy the tropical equations of the Bergman fan, and then collections of rows have to have a certain compatibility condition, which is not that hard to meet. So we call this matrix the diagram of the toric matroid bundle. So here are two examples. If you take this matroid we talked about earlier, the uniform matroid, and you take the 3x3 identity matrix, that's like my favorite matrix. That makes the what I'll call the tropicalization of the tangent bundle of P2. So you can I'll talk a little bit in a second about how you can tropicalize certain vector bundles over toric varieties. So when you do that with the tangent bundle of P2, you get U23, comma identity matrix. And then here's a fancier example. Oh no, what has just happened? This Harry Potter looking thing is called the phanoplane. It is an example of a matroid which is not representable over certain fields like F3. The way you get a matroid out of here is actually you say, it's probably easier to say what dependent sets are, so things that are in a line are dependent with each other. So if you take this particular matroid and this particular matrix, this is an example of a toric matroid bundle. So this is not a terribly difficult type of design problem to meet. And I think probably you could put any number in for 1 and just any bigger number than that in for 2, and the same thing would work. All right. So now let me rattle off some facts about these bundles. Do I have 10 more minutes? Is that how it goes? Okay. I don't know if I'll even need that, so that's fun. So Kumars and I were working on this project at the same time that Diane McClagan and Bivas Khan were working on almost the same objects. So we've coordinated with our papers. They went on the archive at the same time, and I encourage you to read both. So they talk about tropicalizing toric vector bundles. So tropicalization is this process where you take an algebraic object and you turn it into a tropical variety. They tell you how to do that with a toric vector bundle. And when you tropicalize a toric vector bundle, you get a toric matroid bundle. So that's the first justification that there is some actual geometry going on here. These are rightly thought of as tropicalizations of something algebrogeometric.
In what sense is a toric vector bundle algebraic?
I mean, it's an algebraic vector bundle with an action of the torus. That's what a toric vector bundle is. So it is an algebraic vector bundle. Second justification that these things are like something in geometry. They have a sheaf of sections, but this sheaf is not valued in modules or vector spaces or groups or sets. Well, sets, I guess, yes. It's valued in matroids. So in particular, the global sections of a toric matroid bundle is a certain direct sum of flats of the matroid M that one can compute from that diagram D. And these bundles, because they have a notion of global sections, and they have a notion of fiber, and they have a notion about how you map the global sections to the fiber, they have a notion of globally generated. That's fairly natural. And then these are kind of suspect notions because the theory isn't all there yet, but at least in large cases, large families of cases, we know how to say what a nef or an ample vector bundle is. So we have the point is we have notions of positivity which are combinatorial images of the notions in algebraic geometry. All right. Here's some other geometry-like results. If I take an ample line bundle on my toric variety, I can tensor it with my toric matroid bundle, and you just say what happens to the diagram. And then we have some results which are reflective of the same features that happen in algebraic geometry. So if you take the function that sends a non-negative integer to the rank of the global sections of the bundle you get by tensoring your toric matroid bundle with the kth power of your ample line bundle, that will eventually coincide with the values of a polynomial of degree equal to the dimension. And this is an Ehrhart theoretic kind of thing. You can think about it like that. The Euler characteristic makes sense for a toric matroid bundle. And for high K, the Euler characteristic of this tensored up toric matroid bundle will correspond with the rank of the global sections. And so you can view this as a combinatorial version of the higher cohomology vanishes, but we don't really have the higher cohomology. We don't know what it is, but we do have this. It's actually an open question. What is the higher cohomology in this case? And we can also give an explicit bound on when this will happen in terms of the diagram D and the matroid. All right. These toric matroid bundles also have characteristic classes. So we can define turn classes and a K class in the 0th K theory, equivariant, which will coincide with the K classes and the turn classes of a toric vector bundle when the matroid is representable. So if you take a toric vector bundle, it has turn classes and K classes. Because it's toric, they're equivariant. And when you tropicalize that guy, the toric matroid bundle will have the same turn classes and K classes. But the non-representable ones also have a notion like that. All right. So now to finish, I'm going to tell you about a fun thing you can do with a matroid. I swear it's fun. So any matroid determines a diagram, one for free. That just by the theory of the matroid, a diagram which satisfies these design conditions that I've mentioned, you can cook it up. So it should be thought of as a diagram for the permutahedral fan. So what you do is on the row of this matrix that corresponds to a subset S, you put the indicator vector of the M span of S. So you take the span of S in the matroid, and you get a bigger set, you put the indicator vector of that set in for that row. And this will always define, whether or not M is representable, this will always define a toric matroid bundle over the permutahedral variety. And this toric matroid bundle will also always be globally generated and Neff. If M is representable, this construction recovers the tautological bundles of Birgit, Spink, and Seng. So when you do this with the dual matroid, which is a thing I didn't tell you about, you can take a dual of a matroid. You do this with a dual matroid, you recover their QM bundle. And when you do this with the matroid itself, but then you pull it back by something called the Cremona transformation, you get this S bundle. And then for I mentioned when I described Birgit, Spink, and Seng's paper that they combinatorially extend their characteristic classes to all matroids. So we are able to recover those classes as the churn classes and K class of our bundles, of our toric matroid bundles. All right. So that's my argument that these are the geometry that should be put in as an answer to that question. And so I'll leave you with my question right now, which is how much classical positivity theory for vector bundles in algebraic geometry tropicalizes? There's all sorts of results about different types of characteristic classes you can make and ways you can combine them to get positive numbers or log concave sequences out there. And the question is, do those generalize and how? So here's an example. If you fix a Neff class, or an ample class if you like, in the equivariant Chow ring of a toric variety, and you take E to be a globally generated toric matroid bundle, we can make a sequence here with the churn classes and these powers of this class. And the question is it log concave? And the classical algebraic geometry says yes. This answer is yes when M is representable. And so the question is, does that extend to the non-representable case? That's the kind of question I'm interested in going forward. And I think it's probably a reasonable place to stop. So thank you for listening.